Hello there, yous guys. Welcome back. In this video, we're continuing to talk about series and how we can determine convergence or divergence. So in this video, we're going to talk about the comparison and the limit comparison test. So just as a reminder of what we've done up to this point, we've talked about a geometric series in particular and when it converges or diverges. Then we talked about the integral test and the results we can get from that. So in our strategies at the end of these next couple videos, we are going to look at a series, determine if it converges or diverges. We're going to use the test that is most convenient for us or works the best. And this will be one of those tests that we add to our tool bag of convergence testing. And the concept here, I just want to kind of sketch out the concept for a moment. So let's consider that we have, oh, you know what, before I do this, let's do a quick refresher. I just said verbally what we've gone over, but let's write it down. So we know from prior videos, right, that the geometric series, right? So we have that the sum of a r to the n minus 1, which again is our geometric series, converges, right? This is a plus ar plus ar squared, right? Was how we wrote that out. And this converges when or if the common ratio in absolute value is less than 1. And then we also had the p series. So we did this in our last video, and we can justify this with the integral test. So as long as p is greater than 1, the p series converges, and if p is less than or equal to 1, it's going to diverge. All right, now the reason I bring that up is, as we're doing the comparison test, we're going to compare to one of these two known results. Alright, so back to what I was about to say. So let's consider that we have the series, let's see, I'm just kind of making something up here. Let's say we have 1 over n squared plus 1. Let's just kind of start off simplistic. All right, now we know, or we could intuitively guess, right, hunch guess, that seems like 1 over n squared plus 1 is going to behave like the p series 1 over n squared. So what I like to do here is I like to say, you know, we sort of have a hunch of how this series is going to behave. So 1 over n squared plus 1. Now keep in mind, what determines the convergence of any series is the long-term behavior of the terms that we are adding together. So as we go to infinity, right, the largest term in the numerator is 1. The largest term in the denominator is 1 over n squared. So as n goes to infinity, as we look out at the ends of this series, this is going to behave like 1 over n squared, where this guy here is a convergent p series. All right, so we have a hunch that our series converges, but that's not valid enough. We need to justify mathematically that our hunch is true. Now in the prior video, right at the very end, we actually used the integral test to integrate 1 over n squared plus 1. Go back and take a look at that if you want to. What we're going to do here is we're going to use the comparison test to justify our hunch. So so just exploring a little bit deeper and having a conversation with you. If we think of the sum of these terms here, we know that that is a finite sum. It's a convergent sum. Now, we also know that 1 over n squared is going to be slightly larger, right? So 1 over n squared plus 1 is slightly smaller than 1 over n squared. You know, and one thing we can talk about here is the numerators are the same. This denominator, n squared plus 1, is a little bit bigger than n squared, so the 1 over something a little bigger is going to be a little bit smaller. Now we could do a little bit of algebra here to justify my work, to justify my statement that I just said. Common denominator here is n squared plus 1 times n squared. So it's like I'm multiplying the left-hand side by n squared times n squared plus 1. and I multiply the right hand side by n squared times n squared plus 1. So if I'm doing some algebra to justify this inequality that I wrote, I can see that n squared plus 1s are going to cancel on the left hand side, and I'm going to end up with just n squared. And I can see on the right hand side that n squareds are going to cancel and end up with just n squared plus 1. Now this should be pretty obvious, right? For any n greater than or equal to 1, because that's what our series is, the sum from n going 1 to infinity. So for any n greater than 1, 1 squared plus 1 is 2, that's greater than 1. If it's not obvious to me, I can subtract n squared from both sides here. Subtracting n squared gives me 0. Less than or equal to 1, right? And, check mark. I know that that is true. So, in other words, the terms of the series I'm testing, 1 over n squared plus 1, has numbers that are smaller than 1 over n squared. So the concept here being, we know that when we sum up 1 over n squared, right, so the sum of 1 over n squared is going to be a little bit larger than the sum of 1 over n squared plus 1. Going from 1 to infinity. So if 1 over n squared is convergent, well, it is. We know 1 over n squared is a convergent p-series. Then any sum smaller than that also is going to converge. Okay? So this is the idea behind the convergence test. We could look at this visually as well, just to kind of justify this idea. Let's say I have, 1 over n squared as a function. And then 1 over n squared plus 1 we know is slightly smaller. So let's say, here's 1 over n squared plus 1, let's say. And again, just real loose visualization here. So we know from 1 to infinity that the area under 1 over n squared is finite. That was a convergent integral in our last section. Right? So since the curve 1 over n squared plus 1 is a little bit smaller, then the area under that curve is a little smaller, and therefore it is convergent as well. It is finite. So that is the idea here behind the comparison test. Now I'm going to write the formal statement in just a moment, but what I want to do is come back and look at something a little bit different. So let's consider divergence here. So now let's consider the sum, and let's just stick with something that's relatively simplistic. Let's say we're going to look at 1 over n minus 1. And let's start n at 2. I don't want to plug in n equals 1 because I get division by 0. So let's start at n equals 2. So let's consider this series. Now we could pretty easily show that my hunch, right, so the hunch that I'm going to get here is that long term, as n goes to infinity, the numerator acts like 1, the denominator acts like n, and we know this is a divergent p-series, or at least the sum of 1 over n is a divergent p-series. Right? Now, it could be pretty easily shown that 1 over n is smaller than 1 over n minus 1. And again, when I compare so numerators are the same. When I compare denominators, n is a little bit bigger than n minus 1. So 1 over something a little bigger is going to be a little bit smaller. And again, I could do some algebra to justify this. If I multiply, both sides by the common denominator here. Right? When I multiply the left-hand side, the n's will cancel, and I'll be left with 1 over... the n's will cancel, right, and my fractions go away. Right? So the n's will cancel, and I'll be left with n minus 1. And then when I multiply n times n minus 1 on the right-hand side, the n minus 1's cancel, and I'm left with n. Excuse me. Now again, for n greater than or equal to 1, right, when I subtract 1 from a number, it is smaller. Again, I could think of subtracting n from both sides, and I get to a statement that negative 1 is less than or equal to 0. That's definitely true. So conceptually here, the terms of the series are a little bit bigger, right? The terms of my series are a little bit bigger than this known divergence series. So when I look at this series, the series that I'm interested in, the series of 1 over n minus 1, is a little bit bigger than the series of 1 over n. So when I add the terms of 1 over n, that sum is diverging, right? So let's say the sum is an infinite sum. It's not converging. Anything bigger will have a sum that is even bigger, that is also diverging. And again, we could visualize this concept. Let's say here's 1 over n as a curve. And then let's say we know 1 over n minus 1 is a little bigger. Again, I'm exaggerating the shape here. So we know from 1 to infinity, let's say 1 to infinity, right, that the area under this curve is divergent. Right? We know that's a divergent p-series. With the integral test, we proved that was true. So the area under 1 over n minus 1 is even bigger. So therefore, it must also be an infinite area. It is also diverging. Now, just want to point out to you here the direction of our inequalities, and then I'm going to write the formal statement. So the series that we were testing in this example, 1 over n minus 1, it was a little bit bigger than our hunch. Or in other words, our hunch was smaller than the series I'm testing. So if I'm trying to show divergence, I want my hunch to be smaller than the series that I'm testing. So again, anything smaller that diverges, anything larger will also diverge. And when I'm trying to show convergence, I need the inequality to be in the other direction. So in our example up here of 1 over n squared plus 1, right, our hunch was bigger. We wanted our hunch to be bigger because the bigger thing has a finite sum. Anything smaller must also be finite. So in just a second, when I write the formal statement of the comparison test, let's keep in mind the direction of those inequalities that we need to work here. Okay, so our comparison test says something like this, right? It says, suppose that we have two series, right? One will denote as a sub n, and the other will denote as b sub n. So we have some infinite series here. So let's suppose these are two series with positive terms. And the reason we want these series to have positive terms is so that we can show these inequalities are true. So we have two series that are positive terms. Now, the way that I like to think of this notationally is the series of a sub n. This is the series that we're testing, and the series of b sub n is like our hunch series. So we're thinking that the b sub n is known. It's either a known geometric or it's a known p series. All right. So we know what the b sub n is. So if b sub n is convergent, and we can show, right, that my series is smaller than the known convergent series, then since my known convergent series is bigger, anything smaller also has a sum that is finite, right? So if b sub n is known to be convergent and I can show that my hunch is bigger, then we would conclude that a sub n converges. I'll say also converges. Right, so that's the first form of the statement, and then for divergence we need the inequality to be the other direction. So if we know that our hunch b sub n diverges, and we can show that that known hunch is smaller, right, then the sum of my known series being infinite, anything larger has a sum that is also infinite. So we conclude in that case that the sum of a sub n also diverges. So the process that we're going to use here is similar to what how we started the video off. We want to look at the series. We want to get a hunch. And we want to be able to show, right, so if my hunch converges, I want to show my hunch is larger than the series I'm testing. And if my hunch diverges, I want to show that the hunch is smaller than the series that I'm testing. So let's take a look at a couple more examples here. So I'm going to do something that's a little bit more intricate and difficult for the algebra to just work out not so nice is what we just saw. So for another example, right, let's consider we have this series, let's say 5 over, let's say n squared plus 4n plus 3, something like that, right? So we're testing this series. Let's say n goes from 1 to infinity. Now we don't really know if the series converges or diverges, right? The instructions would say determine whether the series converges or diverges. So the first thing I'm going to do within the context of this section is I'm going to take a hunch. So I know that as n goes to infinity, the numerator is constant, right? And the denominator has the largest term of n squared. Right? So when I think of the sum of 5 over n squared, I could pull the constant out. And what I really have is a convergent p series. Right? So I got a convergent p series here, right? P is 2, which is greater than 1. So my hunch is that my series converges. So in order to show that that is true, what we need is for my series I'm testing to be smaller than my known hunch. And again, if my hunch is bigger, then anything smaller will also have a sum that is finite. Now the thing here is I don't know if this is true. I'm going to put a big question mark here, right? Is this true? Okay. If this is true, then we have officially justified that my series converges by the comparison test. So now we're just going to do a little bit of work to show or to determine whether this is true or not. So just like I did in the prior two examples, I'm going to think of multiplying both sides by my common denominator. So when I multiply the left-hand side by the common denominator, I get 5n squared. When I multiply the right-hand side by the common denominator, right, the n squared cancels out, and I get 5 times n squared plus 4n plus 3. Now I'm going to divide both sides by 5. That's dividing by a positive, so I don't change the direction of the inequality symbol. And this is why we have the condition that the terms are going to be positive. We want that inequality to work out nicely. So, is this true? And I mean, definitely this is true. When n is greater than or equal to 1, we're going to have positive terms, right? N squareds are equal to each other, and when I add more terms on the right-hand side, that is going to be bigger. I mean, I could subtract n squared from both sides and get to this statement. And again, when n is 1, 2, 3, 4, 5, these are all positive numbers, so, those are greater than 0. I mean, that is definitely true. So, was this inequality here true? We've gotten to a point where we have a true statement. So it is true. So actually, logically speaking, if we're doing kind of a pseudo proof here, we start with the bottom and move upward. So we know that this bottom line is true. Therefore, the one right above it is true, and therefore the one above that is true, and therefore that inequality is true. We don't write it that way, but that's our thinking. So since we've shown this inequality to be true, then I'm going to say thus, my series 5 over n squared plus 4n plus 3 converges by the comparison test. Okay. So that's the general idea here. And I just wanted to pick something that was, not as pretty. Let's look at another example, and this time I'm going to do divergence. Okay, so let's do divergence. All right, let's see. So I want to pick something that's not a p series. So let's look at this series. Let's look at the sum of 1 over 2 to the n minus 1, and let's say n's going from 1 to infinity. All right, so our hunch in this case is the leading term in the numerator is 1, the leading term in the denominator is 2 to the n. And this is, 1/2 to the n, which is a convergent geometric series. Right, and the reason it's convergent again is my common ratio is 1/2, and that is less than 1. So it is convergent. Right? So my hunch here is that it behaves like a convergent series. So what I need to do in that case is show, very similar to the last problem, I need to show that my series I'm testing is smaller than my known convergence series. Okay? So, question mark, right? Is this true? Right? So to show convergence, I need this to be bigger, right? Because if 1 over 2 to the n converges, anything smaller must also converge. So is this a true statement? Right? So let's work through the algebra and see what we get. So again, I'm going to multiply left-hand side by the common denominator, and I'm going to end up with 2 to the n. Then I'm going to multiply the right-hand side by the common denominator, end up with 2n minus 1. Now when I get to my statement, I should see, right, that this isn't true. Right? So if I have 2 to the n minus 1 is going to be smaller, not bigger. Right? So, if I subtract 2 to the n from both sides, I get to this guy. 0 is definitely not smaller than negative 1. So I get a big, right? So you got to hold up your arms and make a big loud buzzer noise. So this is not true. So in other words, my inequality that I needed to be true isn't true. Now, the one thing we want to be careful of is this doesn't mean that the series isn't convergent, right? It doesn't mean my series diverges. It just means that the comparison test doesn't give me a result that justifies what my hunch shows. And what I want to be careful of, right, common mistake in this class is to say, oh, well, even though that didn't work out, I just know the hunch converges, so this converges. We still have to officially justify the behavior here. So in this type of situation, what we would actually do is what we call the limit comparison test. Right? So we're going to use the limit comparison test. So let's discuss what that says. So I want to write out the formal statement of limit comparison test. I want to look at an example and then justify why the limit comparison test works. So let's first of all write out the limit comparison test as a statement. So it says something like, suppose a sub n, the sum of a sub n and the sum of b sub n are series with positive terms. Right, a series with positive terms, okay? And I'm, technically looking at infinite series here. So we have series with positive terms. So we're going to say something like this. We're going to say if the limit of, so we're going to look just at the terms. So again, in our notation, the b sub n is the hunch. We know how the b sub n behaves. The a sub n is what we're testing. So if this limit turns out to be some finite value. So let's say our limit is equal to some finite some number c, then both series behave the same. Okay. So again, if my hunch b sub n is convergent, when I build this limit of this ratio, and that turns out to be finite, then my a sub n also converges. And then if my hunch b sub n is divergent, I build the limit of this ratio, turns out to be a finite limit, then my series I'm testing, a sub n, also diverges. Again, I'm going to come back in a minute and we're going to talk about why this is the way that it is, but let's look at an example. So let's look at that last example that we were working on. We knew, we had a hunch, I don't want to say we knew, we had a hunch that 1 over 2 to the n minus 1 converged. But we were not able to show that that inequality was true. So again, I just want to remind ourselves, we had the hunch that this was behaving like 1 over 2 to the n, and that was a convergent geometric series. So if I'm following the language of the limit comparison test, the limit comparison test says what I want to do is look at my series I'm testing. I'm going to take a limit of the ratio of that and my known series. Just trying to draw a big fraction there. Now what I want to occur is once I'm done evaluating this limit, the limit turns out to be a finite value. Right? So I'm going to flip and multiply here. So when I flip and multiply, I get 2 to the n over 2 to the n minus 1 as n goes to infinity. And so let's go ahead and evaluate this limit. Let's work through this. Now, if I look at the numerator and denominator, this is like an exponential, 2 to the n, and that's going to go off to infinity. And then, 2 to the n down here is going to also go off to infinity. So what I'm going to do is use L'Hopital's rule to evaluate that limit. I love L'Hopital's rule. Now I take the derivative of the numerator. The derivative of 2 to the x is 2 to the x times ln of the base. And again, derivative of 2 to the n, we're not really doing 2 to the x here. Derivative of 2 to the n is 2 to the n ln 2. Now in this scenario, this is 2 to the n ln 2 divided by 2 to the n ln 2. This is something divided by itself, which is 1. So I'm looking at the limit of 1, and the limit of a constant is the constant. So what we get in this case is a finite value. Right? This is a finite number here. So since my limit is finite, then both series behave the same. Right? So I'll say, since a sub n over b sub n equals some finite number, then both series behave the same. Okay? Both series behave the same. And I'll just go ahead and say, thus, my series 1 over 2 to the n minus 1 converges. Right? So the beauty of the limit comparison test is that I don't have to dwell on that inequality. I know that my series is going to behave, well, I think my series is going to behave like my hunch. Still have to justify that. And with the limit comparison test, I don't again have to really worry about that inequality. If that inequality doesn't turn out to be true, doesn't mean that it's invalidating my hunch. I can come back and use the limit comparison test. So for me personally, if I'm thinking of a flow chart and I'm given a series and I'm asked to test it, in my flow chart, if I'm thinking the comparison test would work, I'm going to use the limit comparison test instead of what I'll call the direct comparison test. So instead of dwelling on the inequality, I'm going to jump to the limit. Let's look at another example, and then we will come back and justify why this limit comparison test works. So I want to look at an example where we get divergence. So let's say we have square root of, we have the sum of square root of n over n plus 1, let's say. Say n goes from 1 to infinity, and we want to determine whether this converges or diverges. So again, we don't know. We want to determine that. So I'm going to have my hunch, and in the numerator, have square root of n that's going to dominate. So I have n to the 1/2 that will dominate, and I have n in the denominator that will dominate. And this turns out to be, if I combine like terms, if I divide like bases, I get n to the negative 1/2. So divide like bases, subtract exponents. So I really have 1 over n to the 1/2 that I'm comparing to, and this is this is a divergent p series. My p is 1/2, and that's less than 1. So this is a divergent p series that I'm comparing to. So instead of dwelling on the interval, the inequality, right, let's look at the limit of the two. Right? So what I'm going to do in this scenario is I'm going to take the series that I'm testing, and I'm going to write the radical as a 1/2 exponent. So here's the series that I'm testing, and I'm dividing by my hunch series. Take a limit as n goes to infinity. And again, my hope is that this limit turns out to be a finite value, therefore the series behave the same. So I'm going to flip and multiply. I'm going to go ahead and evaluate this limit. So if I flip and multiply, think what's going to happen here. I'm going to multiply the n to the 1/2 into the numerator. So I'm going to have n to the 1/2 over n plus 1 times n to the 1/2 over 1 when I flip and multiply. And so that is the limit of n over n plus 1 as n goes to infinity. I'm personally a fan of L'Hopital's rule. Right? This is infinity over infinity. So I'm going to do L'Hopital's rule. Derivative of the top is 1. Derivative of the bottom is 1. So limit of a constant is that constant. Now I want to caution you for a moment here. Both of the problems we've done here, the limit turns out to be 1. That's not always the case, all right? That's just coincidental here. That limit could turn out to be 7. That limit could turn out to be pi. A limit could turn out to be e cubed, right? Whatever that limit is, as long as it's finite, they behave the same. Right? So this is a finite value. So I'm going to say which is finite, and thus I'm going to say the sum of my series that I was testing diverges by the limit comparison test. I'm going to get lazy and say LCT, by the limit comparison test. And what I just thought of, in my prior example, did I say limit comparison test? All right, I scrolled back up real quick. I didn't say limit comparison test, and I actually made a little bit of a righto here. Let me fix my righto. Get it? Get it? It's not a typo. It's a righto. So if I say this guy, that's really me saying the limit comparison test. Right? So let me just fix that in my prior example. So since the limit of a sub n over b sub n is finite, then both series behave the same. And then I didn't write it exactly that way down here. I just showed the work of the limit, and I said which is finite and thus converges by the limit comparison test. All right, just wanted to make sure I was stating that appropriately. All right, so let's do a quick little sketch of the proof of the limit comparison test. And I don't want to get into the nitty-gritty weeds, but let's discuss kind of big picture of why this works. So keep in mind what we're wanting is the limit of a sub n over b sub n to be some finite value as n goes to infinity, right? And what the limit comparison test says is that if b sub n, if my hunch is divergent, then this being true shows my series a sub n diverges, and then vice versa. If b sub n is convergent, then this ratio is finite, shows that my series a sub n is also convergent. So c is a finite value. Now, my prior couple of examples, this c value was 1, but as I mentioned, it doesn't have to be. C is finite. So in the sketch of the proof, what we say is something like this. I mean, we say, like, suppose that we know this number c as between some finite number m, capital M, and some finite number little m. Right? So, if c is the number 5, then we know 5 is less than 6 and 5 is greater than 4. All right? So whatever that c is, we know it's finite, and it's between two other finite numbers. So in other words, as n goes to infinity, this limit a sub n over b sub n is equal to c, right, as n goes to infinity. Right? Now, m is bounded above by m, and if I come over here for what I just wrote, let's say I multiply both sides by b sub n. Right? So a sub n is equal to b sub n. Now, if c is smaller than m, c is smaller than cap m, like we wrote right here, then what I have is a sub n is going to be smaller than cap m times b sub n. So what we end up with here is the actual direct comparison test. Because if b sub n is converging, then it is bigger than a sub n, and therefore a sub n is also converging. So if b sub n converges, so does a sub n, right? Now, if we think the other way, right, if b sub n is diverging, right, if I come back here, and if b sub n is diverging, I have, when I multiply both sides by b sub n here in the middle, right, if b sub n is diverging, then, c times b sub n is equal to a sub n as n goes to infinity. So I jump to this idea. And then I know c is bigger than little m, some other finite number. So what we're showing in this case is if b sub n is diverging, then anything larger is also diverging. Right? So if b sub n diverges, the sum of b sub n diverges, so does a sub n. So anyway, quick sketch of the proof. Right? If as n goes to infinity, I get a limit of the ratio of a known b sub n and my tested series a sub n. If that ratio is finite, then we could technically show long term that we have a comparison, right, But instead of having to dwell on that inequality, we're going to use the limit process because it's a little more efficient for us. All right, so one last conversation in this section would be error bounds. So if we have a convergence series and we sum the first 10 terms, right, what is the error, right, from that estimation? So I want to look at a couple examples here and talk about how we would make that calculation. So let's come back to something that we've been playing with before, right? So in our prior video with the integral test, we looked at the sum of 1 over n cubed. And we used the sum of the first 10 terms to estimate. And we talked about the error, or the remainder, would be at most the integral from 10 to infinity of 1 over x cubed. Now we found out what that number was when we evaluated all of that. It was 1 over 2 times 10 squared. So that was the maximal value of my error. And that turned out to be 0.005. Now that was the known p-series that we used in the prior video for the integral test. Now let's suppose we are comparing to that series. So let's consider that we have the sum of 1 over n cubed plus 1 that we're testing. So we know our hunch in this case would be 1 over n cubed. And if this is convergent, we want to show that it is slightly bigger than my hunch. And again, we know, numerators are the same. This denominator on the left is slightly bigger, so the fraction is slightly smaller. Right? We know that's true. We could go through the 1 or 2 lines of algebra to show that, like we did prior. So, if I sum up the first 10 terms of this series, right, the sum of the first 10 terms, so again, keep in mind, the infinite sum of this series is going to be at most the infinite sum of this series. So when I sum the first 10 terms in this series, it's going to be at most the sum of the first 10 from our known series. Now again, we calculated the sum of the first n terms up here above. I don't want to discuss that yet. But we know the sums are the same. Sum of the first 10 is at most, sum of the first 10 of the series I'm testing is at most the sum of the first 10 of the known converging p-series. So then the errors of my series I'm testing are also going to be smaller than the errors, right, the remainder of my known p-series. So what we can do then in this case is for my series, for the sum of 1 over n cubed plus 1, the remainder of the first 10 terms is at most compared to the series that we are testing. The remainder of the series that I'm testing is at most the remainder of my known series of this guy up here, right? So the sum of 1 over n cubed, right, is going to be the maximal bound of the remainder of my series, right? And I want to fix this notation here. This is not infinite series. We used the sum of the first 10 terms. That's going to have a remainder that's at most the remainder of the known p-series. And we know that that is 0.005 from our prior work. So for my series I'm testing, my maximal error is going to be 0.005. Now let's take a look at something that's geometric, because this will be cool. This is a little bit different. So we had, what do we have? We had something like 1 over 2 to the n plus 1. So let's say we're looking at this series. Right? And we know this converges, right? We have my hunch of 1 over 2 to the n. And we could pretty easily show that this inequality is true. And in fact, it is bigger. It's not less than or equal to, but it is bigger. So let's suppose we sum the first 10 terms of this series, right? So we know the sum of 1 over 2 to the n plus 1 will be less than the sum of 1 over 2 to the n, and that's the infinite sum. Now let's suppose we're using the sum of the first 10 terms for the series that we're considering. We know that that will be smaller than the sum of the first 10 terms for my known geometric series. Okay. So again, what that means in this case is that the remainder of the first 10 terms for my series I'm testing is going to be less than or equal to the error of the first 10 terms of this geometric series. Now we're going to think of this a little bit different. We have not used the integral test to show convergence for 1 over 2 to the n. We know that that's a geometric series, and because r is 1/2, right, it is a convergent geometric series. So I can't use that integral that we just wrote on the prior problem from 3 minutes ago. I have to use the result of the geometric series. Now, here's the scenario that we're looking at. So I'm looking at 1 over 2 to the n. Let me scroll back up a little bit. I'm looking at 1 over the 2 to the n right here. So let me circle this in green. Right? I'm looking at 1 over 2 to the n, and I'm really looking from 1 to 10. Right? What I've done here is I've summed from 1 to 10 of my series 1/2 to the n. Now, if I've summed from 1 to 10, then the error is all of the unused terms from my 10th partial sum. So the unused terms are from 11 to infinity. All the neglected terms is the error of that known convergent geometric series. So my series that I'm testing is at most the sum of the unused terms of that known geometric series. Now, here's the cool thing about this being a geometric series. Again, I'm not using the integral test here. I know the sum of a convergent geometric series. The sum of the convergent geometric series is A over 1 minus r. Now, in our prior video from 11.2, right, A is the first term in the series. Now, the first term in this series is when n equals 11. So the A value is when n equals 11, and I'm going to have 1 minus r, right, and our r is 1/2. All right, so for the series that I'm comparing to, let me switch back to blue, its error is at most the sum of that geometric series. And then I can clean this up a little bit. Switch back to green. I really have, what is this, 1 over 2 to the 11th divided by 1 minus 1/2 is 1/2. And then if I flip and multiply, I'm really getting 1 over 2 to the 10th. Right? The 2 and the 2 to the 11th simplify to 1 over 2 to the 10th. So the remainder, my error of using the first 10 terms of the series I tested, compares to the remainder of the known convergent geometric series 1/2 to the n. Now, if I take out a calculator, this is about 0.000977 if I round. Now, this is pretty small compared to what I might get from a p-series. Now, when we think about convergence of a p-series, that's, polynomial-esque, and a geometric series is exponential-esque, right? So exponentials grow much faster than polynomials. Now, I'm not really thinking about growth here. I'm thinking about convergence. So when I look at a geometric, the terms are going to go to 0. Right, when r is less than 1, the terms are going to go to 0 much faster than like a 1 over n squared. So a geometric series is going to converge quicker than a 1 over n squared, than a p-series. So we're going to typically see the errors of geometric be smaller. So if we're summing the first 10 terms of a p-series, Compared to the sum of the first 10 terms of a geometric, the error in the geometric is going to be smaller in comparison when I'm only looking at, first 10 terms, first 20 terms, first 50 terms. All right, this finishes the conversation for section on comparison and limit comparison test, and then discussing errors. I will see you guys in the next video.